Good day. I'm Norman Wildberger. Today we're going to look at lines and parabolas from the point of view of calculus. So in a standard treatment of the subject, where you learn some analytic geometry involving coordinates x and y, we learn about the idea of expressing a linear relationship by a line in the plane. So we talk about lines in the form y equals, say, 3x minus 4. Or an alternate way of thinking about that is to rearrange things to bring everything on one side. Say 3x minus y minus 4 equals 0. And that's not the only kind of line. We could also have a line that's just y equals something, like y equals 5, or say x equals 14. These are all examples of lines in the plane in an analytic geometry kind of framework. Going up one step, we get parabolas, which are second-degree curves of the form y equals, say, 5x squared minus 4x plus 1. Or perhaps x equals 3y squared plus 2. Now, lines and parabolas are very familiar objects in high school, and students, of course, know lines that look like this, and parabolas are some kind of U-shaped curves that are usually sort of rather quickly drawn, sort of like this, and they can be rather wide or they can be rather narrow, like that one too. The kinds of parabolas that are studied here are rather of a special form. They're ones that are lined up, either up or down. So a parabola of the form y equals something like a quadratic expression in x would be something like this, or something that opens downwards. While this kind of expression usually represents a parabola that opens either to the right or to the left. Now, of course, parabolas are a special case of a conic section, going back to the ancient Greeks. The idea being that we take a cone, like this cone here in blue, and we slice that cone with a plane. And depending on the inclination of the plane to the cone, we get different kinds of conic sections. We could get ellipses, or hyperbolas, or parabolas. And the parabola is a very special case when the plane that we're slicing is parallel to one of the lines of the cone. That way we get a one-sided figure which is unbounded. If you move it just a little bit like this, you would get an ellipse. If you moved it just a little bit like this, you would get a hyperbola with two branches. So a parabola is a very special kind of conic section, sort of poised between the ellipses and the hyperbolas, just sort of on a knife edge between the two categories. From a geometrical point of view, a parabola appears as a rather special object. But from the point of view of analytic geometry that we're going to be talking about today, it's actually very natural and fundamental kind of second-degree curve. Now, the usual story that you learn in high school and in college is that these things should be regarded as functions. So we should think of y equals 3x minus 4 as a function of x. Or we should think of y equals 5x squared minus 4x plus 1 as a function of x. In this case, a linear function. In this case, a quadratic function. This is unfortunate. And I remind you that you can have a look at Math Foundations 42, A and B, where I discuss the problems, the very significant problems with defining what exactly we're talking about when we're talking about a function. So it doesn't make sense to think that we already have this idea of a function, and then a linear function or a quadratic function is something contained inside that concept that's already well defined. So our approach is going to be to not think in terms of functions. We're not going to take this point of view. We're going to rather think of lines and parabolas in this analytic geometry context as being essentially polynumbers. Polynumbers of degree 1 and polynumbers of degree 2. And that's all. So they're not functions. They are just polynumbers. So recall that a polynumber or a polynomial pretty well the same thing. P is constant precisely when its degree is 0. It's linear precisely when its degree is 1, and it's quadratic precisely when its degree is 2. So a degree 0 polynumber is just a single number in the polynumber list. And in standard alpha form, we would just write that as A. A linear polynumber has 2 entries where the second one is non-zero. So it's actually of degree 1. That's sort of degree 0, degree 1. And we would write that in standard alpha form as A plus B alpha. So a quadratic polynumber is one which has an A, B, C, like that form, where the C here in the second coefficient place is non-zero. In standard alpha form, that would be A plus B alpha plus C alpha squared. Now it may take some little getting used to the way we're writing this line essentially in this parabola. So the form here is A plus B alpha, not B plus A alpha. And here the form is A plus B alpha plus C alpha squared. So if it was X instead of alpha, we would say A plus BX plus CX squared. It's much more usual to call the coefficient of X squared A. So the usual form for a parabola is AX squared plus BX plus C. Okay, so we're reversing the coefficients because we have this orientation that the coefficient 0 term is really where we start. And as we progress down the list, we're getting higher and higher coefficients. Then the thing is becoming more and more complicated. So for us, the start of the polynumber is really here at the constant term, and that's why our indexing is going in this direction. We'll see later on that that's actually quite a useful terminology notation. And also later on we may adjust things a little bit. Instead of using A, B, and C, we might use A0, A1, A2, and so on instead. Now, throughout this discussion, you have some choice as to whether you want to work over the integers or, say, over the rational numbers. So you can think of these numbers A, B, and C as being integers or rational numbers, and typically, generally, we'll try to work in the rational number framework, but sometimes integers also. Most of our examples, the numbers will be integers. All right, so we're going to look at these three sort of categories here, and naturally the first one is the constant polynumbers. They're very simple. They are just essentially numbers. So the arithmetic of constant polynumbers is just exactly the same as the usual arithmetic of ordinary numbers. And when we represent a constant polynumber in a graph, say this one here, the constant polynumber 2, well, what are we doing? We're plotting points where the first coordinate is some number c, and the second coordinate is the polynumber evaluated at c. Now if I evaluate this polynumber at c, I get 2, no matter what c is. So all the points that I'm plotting are going to have y-coordinate 2. 0, 2, 1, 2, 2, 2, 3, 2, minus 1, 2, minus 2, 2. If we had rational points, say 3 halves, it would also be 3 halves too. So all the plotting points end up being on this horizontal line. So a constant polynumber gets represented pictorially as a horizontal line. It's a line, but it's a special kind of one. It's a horizontal one. So when we go up one level to degree 1 polynumbers, we have a bigger story. There's more to say. We're talking now about linear polynumbers, which are general lines. So the typical one is something like AB, in standard alpha form A plus B alpha. And to ensure that the degree really is 1, this constant B had better be non-zero. So for example, 1, 2, which in standard alpha form is 1 plus 2 alpha, that's a linear polynumber. And such an object represents a line. but not quite every line. Okay, but most lines are linear polynumbers of this kind. This one here, let me remind you how we plot it. We let alpha be various values, and we calculate the value of p for those various values, and then we plot the value c together with the value p of c. So when c is 0, then the value is 1, so we plot 0, 1. When c is 1, the value is 3, so we plot 3. When c is minus 1, the value is minus 1, so we plot minus 1. And we get a sequence of points like this, moving each time 1 over 2 up, 1 over 2 up, 1 over 2 up as we move to the right. And of course, to the left, down 2 at every step. So we're getting that line there. Now the two coefficients, the 1 and the 2, have a natural and important geometrical interpretation. What's the meaning of this 1? Well, that's the value that you get when alpha is 0. In other words, it's the coefficient of y right above the x equals 0 point. That's usually called the y-intercept. So here the y-intercept is 1 because the 0th coefficient of this polynumber is 1. And what is the significance of the 2, the first coefficient? Well, it's the slope of the line. And what does that mean? Well, if we go over 1 in the x direction, then we have to go up 2. Go over 1, up 2. That means that 2 is the slope. It's how much you have to go up, or perhaps down, with every step of 1 over to the right. If this slope was negative, it would mean that if we go over 1, then we would go down 2. So another way of saying what that slope is that it's p of 1 minus p of 0. If you plug in 1 here, and then you plug in 0, and you take the difference, then this one here will disappear, and you'll just get 2. That's an algebraic way of saying it. So we have the y-intercept of p is p of 0, and the slope of p is p1 minus p of 0. Okay, and in general, if you have a plus b alpha, then the y-intercept is this number a, and the slope is this number b. So it's sort of interesting that originally when we were studying polynumbers, we didn't really think of these coefficients as having geometrical meaning. Now we see that when we're graphing these polynumbers in this fashion, these numbers do have a very natural and useful geometrical interpretation. That's pleasant for us because we are visually oriented and we like to work with lines. Lines are very important kinds of mathematical objects. Let me point out that there's two kinds of lines that we're not getting here. First of all, we're not getting horizontal lines. They are not linear polynumbers. Horizontal lines are special because they're the cases where the b is 0. Back to that earlier example of constants. That's a special case that's actually degree 0. And the other kind of line that we're not getting is a perfectly vertical line, like this. That's not represented by such a polynumber because for every value of x, there's only one value of y that we plot, namely the value of the polynumber at that point. So there's no way that we can ever get a vertical line as a linear polynumber. So linear polynumbers are always non-horizontal and non-vertical. But any non-horizontal or non-vertical line can be represented as a linear polynomber. So now that we're representing polynumbers geometrically, we can apply geometrical concepts to polynumbers. And for lines, a very natural geometrical concept is the idea of parallel lines. What does that look like algebraically? Well, here's line P, which is 1, 2, or 1 plus 2 alpha. And here's a line Q, which is minus 4, 2, or minus 4 plus 2 alpha. These lines look parallel, and they are. And we can see that by looking at their slopes, actually. It's the slopes that determine parallel lines. Because this 2 means that if we go over 1, then we have to go up 2. And this 2 here means that if we go over 1, we have to go up 2. So the slopes are the same. Those lines really are parallel. This one has a y-intercept of 1. This one has a y-intercept of minus 4. Another interesting geometrical notion is that of the x-intercept, the coordinate on the x-axis where the line crosses the x-axis. Now, for a linear polynumber, they're all non-horizontal, so each one of them has to cross the x-axis somewhere. And to find that x-intercept, well, we're looking at the x value here so that the polynumber's value at that point is 0. That'll guarantee that the point that we plot actually is on the x-axis, has a y-coordinate 0. So we're really solving px equals 0. Here, if we set this equal to 0 and solve for alpha, we would get minus a half, which is the coordinate there. And if we set this one equal to 0 and solve for alpha, we would get 2, which is this coordinate here. Here's another pair of lines, R and S, and they also look parallel. And R is minus 2/3 minus 1/3 alpha, which is now a little bit new because we've got some rational coordinates there. But we can rewrite this as a ratio of one integral polynumber divided by another integral polynumber. In other words, a rational polynumber. So this is just another way of writing this rational polynumber. Let me remind you that we said that the rational polynumbers were the second most important field in mathematics, because we can do all of the operations within that context. So this kind of object, the same things apply. It has y-intercept minus 2/3, which would be about there. It has slope minus 1/3. So that means if you go over 1, you go down 1/3. Over 1, down 1/3. And its x-intercept here is minus 2. If you set this equal to 0 and solve for alpha, you would get minus 2. And here is S, this one here, which is 2 minus 1/3 alpha. It's parallel to this one because the slopes are the same. They're both minus 1/3. This one has a y-intercept of 2, and if you write it this way, you can see that the x-intercept is going to be 6 out here somewhere. So the idea of parallel lines is very simple. You just look at the slope, which is the first coefficient. Now let's think about perpendicular lines, which of course is the other standard idea comparing lines. What does perpendicularity look like in terms of the algebra? There are, in fact, quite a number of different possible definitions of perpendicularity. We're only going to talk about the standard one here, but if you are interested in other types of perpendicularities, some coming from relativistic geometry, you can have a look at my chromogeometry videos, which are in the Wild Trig series from 53 to 57. There's not just a blue perpendicularity, which is the usual one, but also a red and a green one, and they interact in a remarkable way. So our standard notion of perpendicularity, you'll agree this is perpendicular to this, and if you look at it, this vector here is the vector 2, 1 in round brackets to denote a vector. Here's the vector minus 1, 2, and these are perpendicular vectors. More generally, the rule is that to get a vector perpendicular to AB, you interchange them and put a minus sign in front of one of them. Say minus BA. Now over here, this line has slope 1/2, because if we go over 1, we go up 1/2. And this line has slope -2. The 1/2 here is this divided by this, and the -2 is this divided by this. So in general, the slope here will be b over a, and the slope here will be a over minus b. And so the relationship between those two slopes is that one is the negative reciprocal of the other. In other words, the two slopes, b and d, of the two lines, if we write them as polynumbers, will multiply to -1. Okay, so just make sure you agree here. The slope here is 1/2, the slope here is -2. You multiply them together, you get -1. And that's the same as here and here. b over a times a over minus b, you get -1. This is coming from geometry, right? If we were just working with polynumbers, it didn't occur to us to say, oh, it's perhaps interesting if we have linear polynumbers when this number times this number is equal to -1. It wasn't clear that that was an interesting thing to do. But now we see that with this representation of polynumbers as lines in the Cartesian plane, this condition is interesting because it corresponds to something that's very important geometrically, namely perpendicularity. There's one more important thing to say about lines before we leave them, and that's a formula for the meet of two lines. So we've talked about this before when we were talking about geometry in the Cartesian setting. We already talked about lines as geometrical objects, like they were things of this form here. And we talked about formulas for the meet or the intersection of two lines. So it's a similar story here, but now we're talking about everything in terms of a polynumber p. So let's first of all introduce a notion of incidence. When a point, say xy, lies on a polynumber p. We'll say that xy lies on p, which is a plus b alpha, precisely when y equals a plus bx. In other words, this is exactly the condition that this be a point that we use to plot this polynumber. If we replace alpha with x, then we get p of x right here. So if this is actually p of that, then we'll say that this point lies on the polynumber. That's an algebraic reflection of the operation of drawing a point and saying that point lies on the polynumber, or is part of the graph. Now, this particular relation, it's a linear relation, it can also be rewritten as bx minus y plus a equals 0. And if you go back to Math Foundations 24 and have a look at lines, you'll see that this kind of linear equation is represented by the line that we called b to -1 to a, with some pointy brackets representing a Euclidean line. So whether we're talking about this polynumber a plus b alpha, or we're thinking geometrically about this line, we're talking about two things which are pretty close to being the same. They're not really the same, but we can certainly, in our minds, compare them and think of them as being effectively the same. So in this video, we stated an important theorem, the meet of lines theorem, and now I'm just going to restate that theorem in terms of polynumbers instead of lines. So if you have two polynumbers, P1 is A1 plus B1 alpha, and P2 is A2 plus B2 alpha, and they're not parallel, so in other words, the two slopes, B1 and B2, are not equal, then there is exactly one point which lies on them both. Namely, here it is. Here's the unique point which lies on both of these two linear polynumbers, or lines. The x-coordinate is a1 minus a2 over b2 minus b1. The y-coordinate is a1 b2 minus a2 b1 over b2 minus b1. And you can see why we require the slopes to be different, because if they weren't different, we would be having zeros here in the denominator, which is not good. All right, so I'm going to leave this to you as an exercise. Please compare this with the formula in Math Foundations 24 for the meet of lines theorem stated in terms of lines like that. It's very instructive to compare these things. All right, so those are really the main things that high school students learn about lines. Okay, lines are pretty simple things. For us, they're just polynumbers with 2 entries instead of 1. It's one step up from a number. Now it's time to go one step more, to go to polynumbers with degree 2. In other words, parabolas. So going from lines to parabolas, it's a big step up. So let's now introduce quadratic polynumbers, or parabolas. And we're going to derive some of the main facts about them, which follows and is some sense a kind of a review of things that we've already done in the last few videos. So I hope this is more or less familiar to you if you have watched those videos before. But perhaps it'll be a good summary and review of those facts. First of all, what is a quadratic polynumber? Well, it's just a polynumber of degree 2, consisting of 3 coefficients, a plus b alpha plus c alpha squared, and we insist that that third one, the c, be non-zero. And I remind you once again, this is a somewhat non-standard form. Okay, in terms of x, this is a plus bx plus cx squared. And we'll make the same definition that we did for lines. We'll say that the point xy lies on the polynumber p, precisely when? If you plug in x for alpha, you get y. So y is equal to a plus bx plus cx squared. So these are just exactly the points that we actually plot when we're drawing a diagram or a graph of the polynumber. All right, so now what did we do when we had a polynumber? Well, we talked about the Taylor bipolynumber and the subderivatives. It's absolutely fundamental kind of thing for calculus. Let's do it here in this quadratic situation, where we can see everything explicitly and it's instructive. So what is p of alpha plus beta? That's the Taylor bipolynumber of p. It's what you get when you replace the alpha with alpha plus beta, going from a polynumber to a bipolynumber. So we have a plus b alpha plus beta plus c alpha plus beta squared. We expand that out. A plus b alpha plus b beta plus c alpha squared plus c times 2 alpha beta plus c beta squared. And then we grouped those various terms into the ones that don't involve any betas, the ones that just involve a single beta, namely this one and this one, and the ones involving beta squared, which is only this one. Here we see the original polynumber recovered. So this, what we call the 0th subderivative, is just the original polynumber p. This one here is very interesting and important. This coefficient of beta is what we call the first subderivative, or just the derivative of p. Right? So the derivative of p, by definition, is the coefficient of beta in the Taylor bipolynumber. And there it is there. It's b plus 2c alpha. So it's this thing here without an alpha plus 2c times alpha. And we also can read off the second subderivative, which is the coefficient of beta squared. In this case, it's just the polynumber c, the constant polynumber c. So these are the two subderivatives of this quadratic polynumber. It doesn't have any more subderivatives, or the other subderivatives are all 0 past this point. Now the Taylor bipolynumber was symmetric in alpha and beta. So we can interchange the alphas and betas in the previous equation and write it now as a combination of powers of alpha. So we're just replacing alphas and betas in the previous. Well, now what we're going to do in the next couple steps is very important. Okay, so make sure you understand what we're doing here. The next step is just a rewrite where we're going to replace beta, which is a Pauli number, with a number. And let's use the number r. Previously for a constant I was using number c, but that's not going to work too well because there's already a c in our equation. And d is not going to work either because in a little while we're going to go to cubic Pauli numbers that are going to have c's and d's as well in their coefficients. So r is nice and safe. We're not likely to get up to that very soon. So r is a constant. Replace beta with r. Just there's r's, there's an r, and there's no thing there. Okay, so this is just another equation. This is now an equation just involving a Pauli number, simple Pauli number in alpha. And now what we're going to do is we're going to replace here alpha with alpha minus r. It's a translate of this. And when we replace alpha with alpha minus r, well, this becomes just alpha. And the alpha here becomes alpha minus r, and the alpha here becomes alpha minus r, and otherwise it's completely unchanged. So just this changes, and this changes. But this is now a very important expression. This is the Taylor expansion of p at r. So we're thinking about r as being a particular value on the line. And this is now a formula that tells us how to evaluate the Pauli number at a random point alpha, just in terms of the differences between alpha and r and the various powers of those differences. This is a very important formula, this Taylor expansion, and what it allows us to do, amongst other things, is to read off the various tangents to a Pauli number. So for a quadratic Pauli number, there's really only one interesting tangent, which is the first tangent, which is what you get when you look at all the things here of degree 1. So the first tangent of p at r is this plus this. We're just dropping the quadratic terms. Now we're going to do some arithmetic. We're going to expand this out as a Pauli number in alpha. It means we have to multiply this minus r here. So there's going to be a minus r times b here, which is conveniently going to cancel with this br here. So there's still an a, but what happens to the cr squared? Why does it become minus cr squared? Well, it's because here also there will be a minus 2cr squared. There's another term multiplying r there. So those minus 2 of them will subtract from the 1 of them to give minus 1 cr squared. And then the terms involving alpha will be just the way they were before. B plus 2cr times alpha. What is this? This is a linear Pauli number. That's a number. That's a number. These numbers involve the original coefficients a, b, and c of the Pauli number and the particular value at which we're evaluating, the number r. So this is a formula for the general first tangent, or the tangent line, to p at r. It's a useful and an important formula because it tells us how to calculate quickly the tangent line to a parabola at any point. So let's look at an example. Here is a Pauli number, a quadratic Pauli number. 5 minus 3 alpha minus 4 alpha squared. Okay, so I'm going to leave it to you to check that the first derivative is minus 3 minus 8 alpha, and the second subderivative is minus 4. This one is half of the second derivative. It's minus 4. Okay, and here's that formula for the tangent line that we wrote down. That's the general formula for a general quadratic Pauli number. If we replace a with 5 and c with minus 4 and b with minus 3, then we get 5 plus 4r squared minus 3 plus 8r all times alpha. So This is a linear polynumber whose particular form depends on what number r we're evaluating that. So we can choose different values of r here, and for every one of those values we can calculate a tangent line to this parabola. Here's the actual value of the polynumber, a graph of the polynumber. Of course, it's a partial graph, as I explained last time. We are only going so far, and this is a rather crude one. I'm only looking at more or less half integral values. And actually the top appears at -3/8. That's when the derivative is 0. Okay, so what do various tangent lines look like? Well, at 0, so at this point here, if we replace r with 0, we get 5 minus 3 alpha. And if we graph that, that's got a y-intercept of 5 and a slope of -3. So it goes down -3, -3. There it is right there. That's the tangent line to P at 0. The tangent line to P at 1, let me check. There it is right there. It's 9 minus 11 alpha. That's the equation of that line. At -1, we get 9 plus 5 alpha. At -3/8, which is right here, we get 89 over 16. In that case, the first tangent becomes actually not a linear polynumber, but rather a constant polynumber. So it's a special case. And in fact, this is a rather important point on this parabola, because that horizontal tangent line means that the parabola has a maximum there. So the fact that we're not getting a linear polynumber, but rather a constant polynumber, is corresponding to the fact that there's something rather special about the point -3/8 for this parabola. And at -3, right over here, the tangent line is 41 plus 21 alpha. Now I want to point something out to you. A rather interesting little observation. Have a look at these two tangent lines. The tangent line at 1 and at -1. These two tangent lines have the property that their y-intercepts are both 9, which means that they meet right at this point here, right on the x-axis, as it turns out, right on the y-axis at the point 9. Now that might be a little bit interesting, because the parabola itself is not symmetrical around this line. The maximum is actually right there. So the thing turns out actually to be symmetrical there, as we'll see in the next lecture. But there's something curious about the fact that if we go equal coordinates away from 0 and take the tangents, we get they're meeting at 0. You can check now that the y-intercepts of the tangent at r and the tangent at -r are always equal no matter what r is. In fact, that's obvious from here. Okay, because the y-intercept is this one here. And if you replace r with -r, that y-intercept is not changing. So it means that if we took the tangent at 3, just somewhere there, and this tangent -3, that they are going to meet exactly on the y-axis. So as a little exercise, you can see if you can generalize that. What's really happening with this phenomena? Can you state a more general fact? We'll see how you do next time. Next time we're going to look at this parabola and parabolas in general in more detail. There's quite a lot of remarkable additional features that parabolas have. They're very fabulous mathematical objects, in fact. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.